All right, hello everybody. Hope you're doing well today. My name is John Belamaric, and I've been working in upstream Kubernetes for a while now, and we wanted to share with you some of the really early things. But this is an alpha feature, but we want to show you some of the interesting things we're working on. And my co-speaker here.
Hi, I'm Sunyanan. I'm working for IBM Research. My research area is about networking, performance optimizations, and this year is my first time to contribute to the Kubernetes.
Yes, thank you. So I guess I should have done this slide while I talked about that. But so what we're going to talk a little bit about is a use case that Kubernetes people have been doing on Kubernetes for a while, but really has been challenging for a number of reasons. So to kind of set up the story, imagine that you've got a network service. And so with this network service, there's a few different components you have in it. And you really need, this is a streaming service, so you really need to have guaranteed bandwidth for your users to be able to get smooth streaming from your service. So these three different components are running in three different pods. And they have some very specific network requirements. So what you would do today in Kubernetes is you might use a special CNI in order to manage the bandwidth allocated to those on your secondary NICs. So you wouldn't be using necessarily the cluster NIC for this. You might be using a secondary NIC for it, but you want to use that and divide up the bandwidth. So as an example, you could use put some annotations on your pod, and you can guarantee the bandwidth to each pod on that NIC. Now the problem with this is that the scheduler has zero visibility into those annotations. And so what can happen is that if you've got a 10 gigabit NIC and your different services in combination may exceed that 10 gigabits, the scheduler will simply schedule them there anyway. And so you end up running out of bandwidth and your users have a poor experience. So how do we solve that? Kubernetes has a feature called extended resources, and in extended resources you can go into a node and you can say, hey, actually this node has a bandwidth resource and it's got 10 gigs of bandwidth on that node. And the scheduler then actually does get that integration, and it can say, so you can, in your pod spec, your container spec, you can say, okay, I require 2 gigabits of bandwidth for this pod, and the scheduler would then be smart enough not to schedule all three of those pods on the same node because it wouldn't have sufficient bandwidth. And that works pretty well as long as you only have one NIC on the node. But if you have more than one NIC on the node, the only way you could do this today would be to create separate extended resources per NIC and kind of have to, go into your pod request and pick a specific NIC for this pod and a specific NIC for another pod. And now you're getting really bespoke configurations between your nodes and your pods, and it's really hard to scale, and it's just extremely awkward. So Pang noticed this problem. I'm sorry, that's her name. So saw what we were doing with dynamic resources, and a big part of what we do with DRA is implement more hardware, give the scheduler more knowledge about the hardware. And so she came to the working group where we're building DRA and said, hey, I have this use case. How can we make this work? And so out of that was born this feature we call consumable capacity. And we're going to talk about that here with the network use case, but it's actually more general than that. Now, you may be asking yourself, what does DRA have to do with network? And I thought it was for GPU. And it is for GPU, but it's for more than just GPU. It's actually a general purpose resource modeling framework and resource requesting framework built into Kubernetes now. So kind of to give the very high level overview, and if you want to learn more about DRA, there's another talk later today around, I think it's at 4:15, is it 4:30? Sometime around there. And we'll talk even more detail, but the very high level, it's basically two new APIs in Kubernetes One is called resource slice, and that's used by hardware vendors to describe their hardware in Kubernetes. And it's a lot richer than the API we had before, the device plugin API, which still works and will forever work. But the device plugin API has basically two fields, a string and an integer, and it's a count of the number of that type of device. But DRA, resource slice, allows the device vendor to describe a lot more about the device, a bunch of metadata about here's what type of device it is, here's how much memory it has, here's how much CPU it has, whatever it may be. And then the second big API in DRA is resource claim. And the resource claim is kind of the way you ask for that hardware. And again, it's a much more flexible API than what we had before with extended resources. Extended resources allowed you to say, I want this string and I want this many of them, and that was it. With resource claim, you can be much more flexible. You can say things like, oh, I want any device with more than this much memory. Or with this new feature, you can actually say, I want a share of a device, and I'll get into that in a minute. The other two parts of DRA are kind of the follow-on machinery that comes with that new describe and request API. Is you have the scheduler has to be able to resolve that request based upon what was described, and then the kubelet has to be able to actuate that request on the node. So those are the other two parts of DRA. So with DRA, one of the core things we started with was the concept of devices being shareable. Now, in the case of, say, a GPU, and we're looking at what's available as of 133 on this slide. This new feature we're talking about was alpha in 134 and also alpha in 135. But the initial concept with sharing in DRA is you have a single resource claim. That resource claim corresponds directly to the allocation of some device or set of devices on a node. And then you can point multiple pods at that claim, and it becomes shared automatically. So the way this will work with, say, an NVIDIA GPU is that as soon as you point a second pod or container at that claim, the NVIDIA DRA driver will configure time sharing and will time slice the GPU, and those two pods will see it in a time slice manner. There's other configuration options you'll have for it to mean something different, but that's kind of the default. That doesn't work at all for network interfaces. Right? A network interface lives in one network namespace, meaning it lives in one pod. If you shared a resource claim that was representing a network interface, like it just wouldn't work. It wouldn't. The second pod would just get no access. So that doesn't work for this use case. We also introduced as an alpha feature, which is also still alpha, something in 133 called partitionable devices. This allows, and what you'll notice here in this drawing, this is the basic sharing. You've got two pods sharing a claim, one connection from the claim to the physical device. In the partitionable devices, we allow the device to be broken up into static partitions, and then you're allowed to treat each of those partitions as if it were a real device. So this is really intended to represent things like hardware layer partitioning of GPUs. Again, doesn't really apply well to a network bandwidth restriction. Maybe you could apply it to like an SRIOV virtual function as opposed to, so the physical function would be there and the virtual function. You could probably apply this there, but that's not our use case. In this one, you'll still see that one claim goes to one of these virtual devices. So from the point of view of the claim, it's still one-to-one with a device here. So what does the new feature do? We call it consumable capacity, and it actually shifts that from there being a direct one-to-one with a claim and a device to allow multiple claims to reference the same device, but allow the platform to kind of regulate the access and the consumption of the resources on the device. The way to think about this, sounds very fancy and abstract, but you do it every single day when you put two pods on a node. You have a thing in the node called node allocatable. Your pod says, give me this much CPU, give me this much memory. A different pod from a different namespace by a different user says, give me this much CPU and this much memory, and we share it on the node. This allows us to do the same thing with a DRA device like a NIC. So now we can say, hey, here's a NIC. The driver is going to create a sub-interface, so we can take those sub-interfaces and we can plop them into two different pods, and we can put bandwidth constraints on each of those sub-interfaces. But the platform, the scheduler, is going to keep track of what those bandwidth constraints are so that we don't over-allocate. And that is how we get to what we're looking for in this feature. Now, Pang's going to go in a little more detail on what actually those APIs look like from both a device vendor point of view and a user point of view, and give us a demo.
Thank you, Sean. Is my on?
Yes.
Okay, cool. So as John has already mentioned, I will go deep dive into the more like implementations, what we changed in the API or what we changed in the scheduler to make this happen. The first thing is related to the first capability that we add with the consumables capacity features, that is to allow allocating the same device for multiple times. As John's already mentioned, until 133, one resource claim, you can link into just only one device, like one-to-one. But with this one, we add a new field into the device, say allow multiple allocations with the Boolean. If this has become true, it will mean that this device can be allocated by multiple resource claim or multiple requests. And how we differentiate it for each resource claim, we add a new field into the stated allocations device that are called share ID, which is a unique ID that we add for each portion or each share. The second thing is that, as you can imagine, like, for example, we have a pod request for 2 NICs. What will happen if we saying we allow we allow one device to be allocated multiple times? Okay, that pod can get the same device, like going to the same NICs multiple times. So this is another thing that we add to prevent that, to make sure that we can get the distinct network card for the same claim or the same pod. So what we add here, okay, sure.
So if you imagine, the point of this is, right, all of a sudden you're allocating the same device multiple times, but what if you actually want to allocate 2 different ones for redundancy within the same claim? So a claim can have multiple requests. We're sort of being a little fuzzy when we say one-to-one. It wasn't really one-to-one, but like you could have multiple requests where you allocate multiple interfaces for the same pod, and then you want to, but the whole reason to do that is availability. Well, if we do that and we get a share, because we don't really need a full 10 gigabit NIC, we just need 2 gigs, but we don't want them to fall in the same physical NIC, because then we get 0 additional availability benefit.
Exactly. So thank you so much for raising this. Yeah. So what we do to allow that is that we add a new constraint. Until now, we have the constraint called match attributes. That is the way that you can do the topology away, I guess, just like the same number of network so GPUs. And
we have a way to allocate. If you're allocating a NIC and a GPU, you want them both on the same PCIe root complex to be able to use GPU direct. So we have this match attributes thing that says, oh, hey, I'm allocating 2 things. Make sure they're the same. In this case.
Yes, it's distinct attribute. Yeah. So it means when we add this attribute, we are going to make sure that the device that we allocate will have a distinct values inside it. And as you can see, that the results will be like this. We put the distinct name, so the allocated one should be like the different name of the device, and of course different share ID. And the third thing is most of the concepts John already mentions about that, to make sure that when we allow a single device to be allocated by multiple resource claim, we have to make sure that their accumulated numbers or the aggregated numbers of the capacity will never over the capacity that we divided in the device. So this is the way that we change something inside the scheduler to make sure that that will not happen. And you can see in these examples, I put the capacity for 10G, like for the egress bandwidth. And we have like 3 resource claim going in. It will deduct it in memory to make sure that if we request more than what is remain inside that device, it will be never be scheduled and try the next device. And this one is not just only for the networking use case. We also see a lot of potential use case that can use these consumable capacity features or like the improvement of the consumable capacity features as well. Like in this one, I'm showing about the networks. We can do the virtual NICs like IP VLAN, MAC VLANs, or we can do the bandwidth limit network allocations. But of course, virtual GPU memory partitioning is one of the main use cases. We can further extend to the storage or even the native resource, like the CPUs, the drivers, and so on. Now it's time for excitement, I guess, or for the demo. Let's see. What would I like to show in this demos will be like in the situations that we have a 3 NICs, HSL 1, 2, and the first one we are supposed to have it infinitely shareable. So everyone can get this one at the primary networks, and we have Ethernet 1 that have a 5G bandwidth, and we have a Ethernet 2 that have a 10G would be considered is like higher bandwidth. And we have 2 requests in the scene. That is the first one request for 5 gigs and the second one request for 8. And the first one is have a less demand. So it say, okay, if the higher bandwidth is available, it will use that. This is utilize another features inside the DRA that is prioritized list, I guess. Right?
Yeah, that's
okay.
great.
I'm not good at remember the feature name, but yes, the first one will be like have a 2 preference. Like if the high bandwidth is available, use it. But if not, okay, any secondary is fine. While we have a second one that do require the high bandwidth. Never give me any secondary that is not have a high bandwidth. Okay, I will check out. I'm not sure whether like it still arrive. See my screen? Okay, I guess it's big enough or. Okay, cool. This one is an example that I have already explained. We have 3 resources in there, and the current step is that I deploy the example drivers, DRA drivers that is running. And then we are going to verify how the resource life look like in the DRA. As you can see here, what is added into the device list is the capacity field. That in this capacity field, in addition to the value of capacity, we can also define the request policy to the capacity this capacity as well. So what is the request policy? Is this the way that you can additionally tell that how the resource claim should consume the capacity that you have? For example, you can define like if your resource claim doesn't give any like clue about how many capacity you need, this should be the default values, or like this should be the minimum value that is have to request, or this should be maximum values and this chunk size or the valid value.
Yeah, and this API is for the device vendors, right? This isn't really a user API. This is like if you're, or the cluster administrator maybe, like this is how I want my NICs to be consumable, like, and it allows us to shape the requests that the users give.
Yes, thank you. And you can see we have Ethernet 0, Ethernet 1 and 2, and in the zeros, you can see the default value is zeros and valid value is 0, so it means user can request just only 0 capacity to make sure that it's infinitely shareable. While the others, you define like the minimum values to make sure that it must consume the capacity. And then I define like the common stuff like a resource claim template, device class that we need. As you can see, it have a primary, secondary, and high bandwidth. Let's see how the device class looks like. In the any secondary device class, what we define here is that any device that is not Ethernet zeros, we consider it is any secondary device. And the high bandwidth device class, what we define is that, further thing is that capacity of the of the egress bandwidth must be more than 10 G. So this is how we define the device class, and now we have 3. And let's see how the claim look like. Okay, we define 4 of them. This is the first resource claim that I mentioned about requesting the 5G and have a prioritized list features inside here. It will say, okay, first availables, if you have a high bandwidth device class, give me that. But if not, okay, give me any secondary. And then we define the first high bandwidth preferred port. Okay. How many minutes? Okay, I still have some time.
You're good.
Good. Okay, what expecting is that this port should get what they want in the first place because there is no port inside here. So the high bandwidth should give to this one. Oh, sorry. Okay, as you can see here, what's given here is the Ethernet 2, which is the high bandwidth one. Now what I'm going to do next is that deploy the second port that require the high bandwidth one. So what we expect is that it shouldn't give that because it's already it's already taken by 5G. We have just only 10, so we cannot give it. This is how the resource can look like. Okay. Yeah, let's verify it shouldn't be running. Okay, and we can further verify the reasons of the pending to make sure that it's not just only the timing stuff. Okay, you can see that there are no availables. It's not can be allocated, so we delete the blocking one, the first one, to ensure that it can become running. Okay, so you can see that it's become running, the high bandwidth required one. And we can verify that, oh, sorry, I can't. Yeah, now it's become reserved for the second port with the 8 gigs over here consume capacity. And again, I forgot to highlight that you can see every time we make a share, it should have a share ID over here. Okay, the last time, okay, we are retry deploying the preferred port again. What we expected is that it shouldn't get the first choice, it should get the second choice. That is the one that any secondary, which is Ethernet 1. Okay. Okay, it's running. Now we can verify what is inside there. Okay, this is inside the first resource claim. Okay, yeah, inside there you will see that it will get the Ethernet 1, which is like not the high bandwidth one, but the second choice of this port. And I think the last thing is to verify is that if you still remember, we share the Ethernet 0 between these 2 ports. So it's linked into the same device. This command is to confirm that it have a different share ID over it. And I think this is the end of the demo that I would like to share. Maybe I will get the mic back to John to wrap things up.
Sure. Yeah. So that was So that's a demo of the feature. It's pretty cool. We've got a ton of things we're doing in DRA, and we'll talk more about this later. This feature box there, and you can see these are this is our plan, one of our sort of high-level planning documents we use in our working group. And you'll see 135, which is not yet released. It's alpha. We have a second alpha of it, which is pretty typical in Kubernetes. And then we're expecting beta in 136. That's our target. Lots of other features we're working on here. If you want to learn more about those, come to the talk later this afternoon, and we'll talk a little bit more about that. So big takeaways. DRA is not just for GPUs. DRA is for any kind of resource management. That's the R is resource. And it's pretty flexible. We're building a lot of interesting features on top of it to do things that you've never been able to do before in Kubernetes. And this is one of them, which is super useful. Feel free to come join us. We are a very open, friendly community if you're interested in influencing the direction of this feature and other related features. So I think that's it. We're ready for questions.
Yeah. Thank you.
Oh, you guys aren't allowed to ask questions.
Hi, thanks for the talk. I just have a quick question about how this interrelates with like partitionable devices, and is there a way? Well, I guess it's a two-part question. The first one is there a way to ask for, say, a full GPU without specifying consumable capacity, assuming it in the future will have the ability to, have slices of memory being able to pull from it? And the second piece is, with something like MIG, I want to have a full GPU or be able to consume some specific amount of memory from it using consumable capacity, or divide it up into a bunch of MIG devices. And how do those things play together nicely?
Yeah, so I think that that'll come down to how you define your sharing request policies. So if you look at those request policies, you can, for instance, say that the minimum is, say you've got a 40 gig GPU, you can say that the minimum is 40. If you want to make it multiply allocatable, right, you could say the minimum is 40, and then you'd always get a whole one. I don't know exactly what.
Sure,
you
but I
want to
guess
do that.
I didn't want to have to necessarily say how much
Right.
memory I want. I just want the full GPU. Kind
Right.
of how you
So
request
because
it
the
today.
default is 40,
Mhm.
then if you don't say, you get a whole one.
You get the whole thing.
But if you do say something, if the minimum, sorry, I should have said minimum, not default, not minimum.
Default, yeah.
Yeah, thank you. So you can control the minimum, you can control the maximum, the default, and you can control the block size. So as a vendor, right? So you could say, okay, I want my default to be the full capacity. I want my minimum to be 0, and then you get kind of somebody who doesn't ask for anything gets the whole thing. Somebody who asks for some small amount, like 0, they could infinitely share it or whatever, right? So.
Yeah, so how that would integrate them with partitionable devices, I guess, is that your full GPU would be modeled like that, and then all the other MIG devices would be modeled as we always do with
You
partitionable
could do
devices
that
today.
however you want.
Yeah.
I mean, you could even
Yeah.
make those shareable, right? There's no
Sure.
reason you can't share a MIG
Okay.
in a
Yep. Good, thanks.
Good presentation. Thank you for the demo. The distinct attribute API and the comparison with the match attributes was interesting in the sense that match attributes has a plural, which is a list of attributes. And in this case, the distinct attribute is a single field or single valued.
Actually, I believe match
attribute is the same.
It's the same. You just
Yeah.
list the same. You just list multiple constraints.
Okay, perfect.
Yeah.
So
it's identical.
So in that case, if this secondary NIC use case is that give me the secondary NIC such that it's not just the same name, but also belonging to a different PCI root, for example, then it should still be possible with this API, right?
You just add another distinct attribute in the list.
Perfect. Thank you. Yeah, I just wanted to make sure that use case was covered. Thanks.
Thank you.
Does the accounting for how capacity is consumed get handled by the DRA implementation or by the vendor driver?
The accounting is all done in the scheduler. The driver does the enforcement. So it does the actuation. The driver takes that information from the scheduler and says, okay, I'm going to limit this sub-interface to this much bandwidth, right? But the accounting has to be done in the scheduler, otherwise we're back to where we were before, that we could over-allocate.
Thank you.
Well, I think one more. We got 15 seconds. Quick.
Go ahead.
So the demo showed that there was a step in between where a user had to delete the pod because capacity was not arranged or optimally allocated.
Yeah.
Do you foresee a use case where a vendor would able to kind of get a signal that I have additional allocation coming in, which could be optimally allocated if I kick this pod out and restart the whole?
That's not a vendor. That would be
Yeah.
like a preemption thing, and that would be more a scheduler feature. So we have preemption models where, like, right, if you've got a pending pod and it's a higher priority than other pods, the scheduler can preempt them. This would be the same thing. The pod would remain pending, and it would see that there's a lower priority pod, and it would boot it. But that's a scheduler thing. It's got nothing to do with DRA. I mean, in DRA we could potentially implement something more sophisticated that's per device, but we haven't thought about that, honestly.
We haven't implemented it because the scheduler doesn't know that evicting the pod will make the device available. It's just not supported right now with DRA.
That is exactly why I mentioned the signal from the vendor is important for the scheduler to know.
I'm not sure if that's enough because the device may be shared among multiple pods, so just evicting one pod's not going to necessarily release the claim.
The scheduler could know, it just isn't implemented.
Okay.
PR's welcome.
Yeah, that's your next project, Leif. So,
Yeah.
All right, thank you very much. I think we're out of time here.